Okay, so momentum and collisions are the practical effect of Newton's three laws. And fun fact, Newton didn't really write the three laws that we tend to attribute to him. He was primarily focused on things like momentum. And I have up here some carts. They're really neat. Remember, the carts themselves are half a kilogram, and I put two 1 kilogram blocks on them. And something kind of neat happens. They have magnets on either end. Whee! This is what happens when an object of one mass strikes an object of the same mass. There's a total conservation of momentum. Momentum is mass times velocity. It's the oomph of things in this world. It's their mass times their velocity. You can have something moving really fast, but not have a lot of oomph. I once shot myself with a ping pong ball traveling faster than the speed of sound. Didn't really hurt much. But if you hit yourself with a normal ball traveling faster than the speed of sound, it's going to hurt a lot. Very small m, very big B. Similarly, it doesn't take a very, very fast bowling ball to really hurt you. A bowling ball can go really slowly because it has a lot of mass. So that's momentum, mass times velocity. This is what happens when an object, we call this the attacker, strikes a target of the same mass. Attacker, target. Kind of cool. Now something really interesting happens when a heavier object strikes a lighter object. What do you think is going to happen when this cart, now twice as massive, strikes this cart, which is half the mass of this one? What do you think is going to happen?
Heavier cart still keep kind of going too?
That's a good guess. Anything else? So Sean suggested that the heavier cart will chase the lighter cart. Anything else?
I'm trying to think of a way to word it, but I think it'll, about however much more the object weighs, it'll like, it's like a ratio. I think it'll go faster the second object.
This one?
Than it did the first time after the energy.
Sounds good. So let's test it. Well, you were both right. The heavier object did chase the lighter object, and the lighter object went really fast in comparison. So it's important to realize, conceptually and mathematically, but conceptually, that when a heavier object strikes a lighter object, that heavier object will chase the lighter object. And it turns out the math works too. What about the opposite way around? When a lighter object strikes a heavier object?
The lighter object kind of go backwards and the heavier one will kind of keep controlling.
Yeah. This is kind of a wild, wild thing. So just like in the animation, when a lighter object strikes a heavier object, the lighter object recoils, and the heavier object still goes. But this is really weird, because when the lighter object recoils, that means more momentum was transferred to the heavier object than the lighter object was carrying in magnitude. Let me give you an example. If the lighter object was carrying 6 units of momentum, and it struck the heavier object and came back with -4 units, how much did the heavier object get? If it came in with 6 and goes out with -4, how much was transferred to the heavier object? 10. 10. Isn't that weird? So yeah, when a lighter object strikes a heavier object, the lighter object is going to recoil. The heavier object will actually move with more momentum than the lighter object was carrying. This only happens in a specific kind of collision called an elastic collision, which we'll talk about in a little bit. Okay. Questions? Yes?
So what if that same thing happens in an inelastic collision?
All bets are off.
Bets are off?
Yeah. With an inelastic collision, energy is no longer conserved. With an elastic collision, energy is conserved. And we'll talk about that. There's a slide specifically for that. Okay, what you have in front of you is called the impulse momentum theorem. This is momentum, as is this. The letter P is what we use for the momentum of a system. Momentum is a vector, a very, very important vector. And it's also important that it is a vector. It's equal to mass times velocity. Velocity also being a vector. Now, when I say something is a vector, what's significant about that? It has a direction, exactly. Now consider this. Have you ever heard of the conservation of momentum? The conservation of momentum is very, very important. And it states that momentum vectors must be conserved. But there's something kind of goofy going on. Golf ball. Okay. And when I drop this golf ball, what direction is its velocity? Down. And if its velocity is down, velocity being a vector, and its mass is a scalar, then what direction is its momentum? Also down. Once it hit and came back up, what direction was momentum? Up, because the velocity was up. Does that mean momentum wasn't conserved anymore? Yeah, that's exactly what it means. It means momentum wasn't conserved. So there had to be something else to make momentum conserved, and that thing was impulse. We'll talk about it in a second. So momentum, given the letter P, is mass times velocity. Now, we've all learned Newton's second law, F equals ma. Newton did not write F equals ma. What he did write was that force is the time rate change of momentum. Write it really big if you can't see it over here. So we say F equals ma. That's Newton's second law, right? So we've always Newton's second law. Well, that's not what he wrote. He wrote mass is the dv dt. Those of you in calculus, you've done derivatives. So if you derive his formula for time, then you get F equals ma. But that's not what he wrote. He said mass times change in velocity divided by a change in time, that's going to be a force. And if you make this velocity this change in velocity very, very small, and you make this time very, very small, that's where you get your force. Mass dv dt. So he said mass dv dt. That's force. Mass times the change. Mass times the time rate change of momentum dv dt. Well, for those who aren't in calculus, if you just take this quantity equals force, and then you substitute over the time, you get mass, change in velocity, equals force, change in time. That is called impulse. Impulse is a quantity like work, where it converts one momentum to another momentum. Just like work converts one type of energy to another type of energy, impulse converts one momentum to another momentum. And it allows us to conserve momentum, even though they might be vector opposites in different directions. Isaac Newton invented calculus for physics. It wasn't like, math is better than physics. Like, math was a tool that was invented for physics. He invented calculus so the physics would work. Okay. Back to my golf ball. I love golf balls. They're really great because they're really good at exchanging energy between them. If I drop this golf ball, what direction is its momentum? Down. After it hits, what direction is it? Up. So we have a downward momentum, which suddenly turns into an upward momentum. So basically, is momentum conserved? No, not if we look at just those two vectors. But what happens is the momentum turns into collision during the collision. Sorry, turns into impulse during the collision, and the impulse becomes momentum again. So all the momentum is conserved into impulse. Then all the impulse is then conserved into momentum, so the momentum gets conserved during the collision. Does that idea make sense? kind of goofy. We talked about how kinetic energy can become potential energy and vice versa via work. Well, momentum down can become momentum up via impulse. Moving objects have impulse. Moving objects have momentum. Colliding objects have impulse. John.
Is impulse like another way of saying thermal energy, kind of being
Nope.
transferred?
Nope, not in the least. It's not energy. These are two very separate things. It's just the transfer of the molecules switching into each other and then squishing out. So what's literally happening is the molecules are getting squished and then unsquishing. During that squish and unsquishing, that's the impulse. It allows us to flip the vectors around. Takes a downward momentum vector, turns into an upward momentum vector via the impulse. Okay. Other questions? Yeah.
So impulse is what preserves the momentum?
Mm-hmm. Yeah. It is what allows the vectors, it is what allows a downward vector to become an upward vector without making the universe explode. Because momentum has to be conserved. You're like, you can't make a downward vector become an upward vector. That doesn't make any there's no conservation there. Well, there is if you put something in between, and that is impulse. So when you're running down the road and you're like puffing and puffing, you got momentum. When you knock over the old lady who's in your way, you have to transfer impulse. During the collision, that was impulse, and you transfer momentum to her through impulse.
Okay.
Momentum, impulse, 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 impulse. Momentum, impulse, momentum. Momentum, impulse, momentum. Ooh, okay. Unless they go off rail. Momentum, impulse, momentum. Get the idea? Okay. So that leaves us the impulse momentum theorem. So F delta T is the impulse, M delta V is momentum, and then delta P is just the symbol we use for momentum. One of the goofiest things, I think, in physics is we like to have named units for things. We have volts, we have amperes, we have newtons, but we don't have a named unit for one of the most fundamental things in physics. The unit for momentum is just kilogram meter per second. Kilogram for mass, meter per second for velocity. That's it. The unit for momentum is just kilogram meter per second. Maybe if you're incredible later on, they'll name it after you. Who knows? Counting, that's it. Yeah. So we got 35 garners of momentum traveling down the road. Yeah. What's the unit for impulse? What's the unit for impulse? The unit for impulse is a Newton second. The unit for mass is a kilogram meter per second. Yeah, it's kind of fun. You're like, a Newton is, remember F equals ma? A Newton is a kilogram meter per second squared. So a Newton second is a kilogram meter per second. Can you see that crazy math? Okay. No. Yeah, there's no named unit for impulse, which is kind of goofy. But that's where we are. Okay, questions? All right. So a large impulse is required for a large change in momentum. If you want to get your car going really, really fast, you're going to have to apply a force over a time to get it going. And any change in momentum you want is going to have to be done with an impulse, whether that being applying the brakes and applying a force in the opposite direction, or hitting the accelerator and applying a force in the forward direction. Whatever change in momentum you want has to have a change in impulse. Large impulse is required for a large change in momentum. Small impulse requires a small change in momentum requires a small impulse. I'll be writing this down. You don't need to write this down. This is like super obvious. I wouldn't write this down. I'd be like, well, yeah, that's one good. Fun question though is, does a large change in momentum require a large force? So, by depends on the mass of the object, what you really mean is yes or no? No. Anyone gone on a cruise yet? Okay, so a few of you have. If you haven't gone on a cruise yet, you're eventually going to have to, because everybody has to go on a cruise and decide whether they hate it or like it. It's the way humanity works. Eventually, you'll have to go on a cruise. As the giant cruise liner, which weighs thousands of tons, comes into port, it starts slowing down, applying a small force in the opposite direction, miles before it even gets to the port. Okay. Really, really long time, because it's a very, very large mass. So, but it doesn't apply a lot of force. It simply doesn't need to bring along a really, really big engine. It doesn't have to. It's not a combat vessel. It doesn't have to go really, really fast all of a sudden. So it goes very, very slowly. But it is still able to stop. And it's still able to leave port and get going. So does a large change in momentum require a large force? No. You can apply a small force, but what? Over a larger time. Over a larger time. Which leads us to car crashes. You get the idea that you can apply a small force over a large time to get a large momentum? Which then leads us to car crashes. Raise your hand if you've been in a car crash. And again, once again, if you haven't yet been in a car crash, you will, somewhere in your life. You'll either be the cause of it or the victim of it. It's going to happen. Some car crashes can be lethal. What is lethal about a car crash?
The impact, like the sudden stop that you hit the car with.
The sudden stop you hit the car with. Okay.
The sudden change in momentum.
Yeah.
The sudden change in momentum. Specifically of what? A large impulse. Okay? So the change in momentum, a large impulse, change in of what specifically?
With the car stopping, but you're not.
Yeah. It's a big deal right now in the 21st century. What specifically is problematic with a car crash? It's not you hitting the windshield. You can hit a windshield. You're pretty tough. You're actually pretty durable. It's certainly not you getting crushed by all the metal. And very rarely does anyone ever bleed out in an auto accident. So what makes an auto accident fatal? It's everything to do with the brain. Your brain has about a half an inch, about a centimeter of goo between it and the skull. Most people's skulls are pretty hard. Okay? Your brain, however, is not. When your brain slams into your skull, some of the brain juice can leak out. That's a problem. If you're lucky, you just pass out and wake up a little dazed and maybe forgetting some things. If you're not, your brain will just stop remembering how to make your heart beat. Yeah, that's a problem. If your brain loses so much brain juice that it can't tell your heart to beat, then you're just done. So, what happens in a car crash? Your brain is moving at the same rate as your skull. And then it slams into the windshield. And your skull comes to a stop, and your brain's like, no, skull! And all the brain juice falls out. That's a problem. How does a seatbelt and an airbag keep that from happening?
The seatbelt makes you stop before you fly out the windshield, or at least hit the windshield, so your head doesn't come to a very hard stop. It's in the air, but it comes back. You're not hitting impact when you go backwards. You kind of bounce back.
Yeah.
On your own.
A seatbelt doesn't keep your brain from colliding with the car. The seatbelt's part of the car. It just makes your brain collide sooner. So instead of going crack, whee, thud, your brain goes squish, 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 squish. It basically makes the collision take a long time, which is good. You want your collision to take a long time. You're going to come to a stop no matter what. Your brain is going to come to a stop no matter what. You want it to just come to a stop for a very long amount of time. So if you have no seatbelt, you have a change in momentum, the time to come to a stop is what? No seatbelt, it's you against the windshield. Windshield's going to win. Very rarely do people ever get ejected through a vehicle through a windshield. Usually if you get ejected from a vehicle, you get ejected from the side, out the side of the vehicle. Very, very rarely do people ever become forward shooting missiles. And when that happens, it was such a catastrophic accident anyway, you probably didn't really matter. You were either going to die when you hit the windshield or when you hit the ground or the car moving that direction. So without a seatbelt, the time to come to a stop is very, very small. Which means the force is going to be very, very what? Big force. Big force.
Big F.
Big F. Big squishy brain F. With a seatbelt and airbag, again, the momentum change is going to be the same. The impulse is going to be the same. But what changes with a seatbelt and airbag? Yeah, bigger time. You start colliding, instead of, if you're right here, your windshield's over there, you start colliding right here instead of over here. You make that collision happen a lot longer, and you're going to encounter a lot less force. Little piquito force. It's like you just get out, rub yourself, dust yourself off. That was cool. No big deal. Which leads us to our discussion about concussions. So concussions are a big deal right now, especially in the NFL. New research is kind of interesting. You probably think that you can hit your head and not get a concussion as long as you stay awake. Is that true? No. A lot of people think that like any collision, like if this is the head hit collision area, any collision, like this is where the concussion is, anything here is safe, anything here you pass out and is unsafe. Turns out not to be the case. There's things called microconcussions, which happen over long amounts of time, small collisions that happen over long amounts of time. You don't have to lose consciousness to have a concussion. You could be totally lucid and aware and still have a concussion. Because new research is coming out, they're like, you don't have to lose consciousness. Your brain doesn't have to basically get that bad to have a concussion. You can have a bunch of small concussions that can build up over time. So please be careful when you're doing your sports. Yeah. You know how to completely, you know how to remove concussions from sports?
Don't play them.
Don't play them. Or, see, the problem with, even if you're in a helmet, your brain is still really close to your skull, and your skull is very, very hard. So if you just cut the skull out, took the skull out, and put your brain in more viscous goo, then you could hit a lot harder, and your brain would be safer. Like if you had this big, huge, like helmet where your brain was just sloshing around in there, you're gonna be okay.
So we're going to remove the top parts of our skull and then fill our helmets with like Jello.
Right, because the skull's the problem. Hitting the skull is the problem. We gotta take the skull out of the equation.
So if we take the skull out, we also make cars more safe too, right?
Exactly.
He's never gotten a concussion with fighting.
Exactly.
Girls.
Okay. You need to write this down. You don't need to write this down because we're going to do a whole bunch of exercises. But just as a matter of mental exercise, consider a 2,000 kilogram truck traveling at 10 meters per second. How much momentum does it have? 20,000 kilogram meter per second. 20,000 kilogram meter per second. So that amount of momentum can be arrested either applying a 4,000 newtons of brakes in 5 seconds, that's comfortable, or 200,000 newtons of force over a tenth of a second by hitting a tree. Either way, that momentum is going to come to a stop.
Well, yeah.
Okay, take a look at this animation. This is an important one. Newton's third law tells us for every action, there is an opposite and equal reaction. Okay. We do that, so we say that so we can have force pairs. But take a look at the bat and take a look at the ball. I'm not trying to trick you. I was never trying to trick you. And I'm not trying to trick you now. But there's something you need to realize about momentum. Bat slows down. Yep.
Bounce back.
And what happens to the ball? Okay. What can you say? Can anyone make a statement about the momentum of the bat, or the change in momentum of the bat versus the change in momentum of the ball? Okay, so Michael said something very profound. The bat loses momentum, the ball gains momentum in the opposite direction? Is that opposite direction the ball is going? Okay, this is what's important. The ball's right directed momentum, so right vector momentum, gets smaller. So it loses right vector momentum, right? The ball has left vector momentum, and then all of a sudden, right vector momentum. The ball gains right vector momentum. The bat loses right vector momentum. The ball loses left vector momentum. The bat gains right vector momentum. For every action, there is a what kind of direction force? Equal directed force. Sorry, I didn't try to trick you, but realize when momentum vectors are gained or lost, they are gained or lost in the exact same direction. The only reason we say every action has an opposite and equal reaction is so you can understand force pairs. But now that you understand force pairs, you must realize when you lose momentum, another object will gain momentum in the exact same direction. Does that idea make sense? Okay, I wasn't trying to trick you. Nobody's trying to trick you. It's just we realized somewhere along the line that in order for you to learn about force pairs like weight and normal, you had to have opposite directed vectors. But with momentum, which is really the effect of Newton's laws, the vectors are gained or lost in the same direction. Capiche? Okay. All right, so a closed system, basically momentum is conserved. So whatever momentum exists at any time must exist at all times. That's what a closed system means. A closed system means we're going to identify the system as a ball and a bat. Whatever momentum exists with the ball and the bat before the collision have to exist with the ball and the bat after the collision. That's a conservation momentum. So bat loses right vector, ball gains right vector. Ball loses left vector, bat gains left vector. Okay. This animation is kind of fun. It doesn't have a lot to do with momentum, but it's just really fun. Now that we're at like that brain is leaking, you know, blood coming out of your ears, healing. You want to watch a fun video?
Yes.
Sure.
Now realize this is super pre-YouTube. Way, way, way pre-YouTube. So the quality is not exceptional, but it's still a fun video.
You can't get through there. No, I can do this. Just chip out. I can get through there. Just chip it out. No, I can get through there. Watch. Okay.
No, the one that goes for it.
Yeah, you're right. I guess I should have chipped out, huh?
Custom clubs for greater accuracy. Chipshot.com.
More!
This is weird. What does he do with his head?
Yeah, you're right. I guess I should have chipped out, huh?
I feel like you should
I'm trying to
to read it.
That's like Grammy, there's like Emmy award winning art there. Like, give that man an Oscar. That is the best pratfall ever. You're falling down to the little arm thing. Okay. Okay. Collision elasticity. There are two types of collisions in this world. There are elastic collisions and inelastic collisions. There's good collisions and bad collisions. An elastic collision is a good collision. The kind of collision that we can calculate very easily and that's very, very pretty. In an elastic collision, all the momentum and the energy are transferred. In other words, no energy is lost in an elastic collision. Whatever energy you have in the system beforehand, you have in the system afterwards. Tomorrow we're going to get some mattresses and we're going to jump over each other in the hallway. Only I have some mattresses.
You think air mattresses would work?
No, it has to be slippery. What if you put like a sheet on them? It's probably okay. Okay, so in elastic collision, objects don't deform, they don't stick together, they don't lose mass, and most importantly, they don't lose energy. Whatever energy this object has, it's transferred to this object. Whatever object energy this one has. In an elastic collision, there is no loss in energy. Now, contrast that with an inelastic collision. In an inelastic collision, objects may deform, they may stick, they may lose energy. Actually, they do lose energy. So in an inelastic collision, there's more energy before the collision than afterwards. Where does it go, Mr. Byers? Usually goes to sound, to heat, as the molecules vibrate. And here's the thing about elastic collisions. We like to pretend that collisions are elastic in real life. In real life, they're not. Billiard balls get close. The Newton's cradle up in the corner, those things get close, but they're not perfectly elastic because they're doing something that tells us energy is being lost. What are they doing? Yeah, they're creating sound. Fun fact. You might have seen the Mythbusters where they tried to make a really, really big Newton's cradle. Does anyone know why that didn't work? They tried to use big steel balls. Anyone know why it didn't work? It's because things don't scale. Energy moves through metals in the neighborhood of thousands of meters per second. Let's just say steel is 5,000 meters per second. That means when the first ball hits, the energy has to travel through the material as molecules get squished together, and the energy travels through the material at 5,000 meters per second. To say that this ball leaves the instant this ball hits would be incorrect. What's really happening is this ball hits, the energy is traveling through these balls, then traveling to this one, then carrying it out. In fact, since energy moves at about 5,000 meters per second through a steel ball, if you had a small planet-sized Newton's cradle, that first ball would hit, let's say they're 5,000 meters in diameter. When that first ball hit, nothing would be happening until a second later when the next ball hit, or next ball left. It would go bonk, and the energy would go and then out after 1 second. If these were 5,000 meters in diameter, this one would wait 2 seconds to leave after this one hit. It would go thud, move, thud, move, because energy is traveling through them. So the reason the Mythbusters giant Newton's cradle didn't work is there was simply too much energy going through the material, causing the material to vibrate too much. Smaller Newton's cradles work best. Anyway, kind of fun. Okay. Questions? where do we see elastic collisions? Pretty much only one place. Not in space, even not in space. It is true that there is no sound in space, but if somebody tapped on your helmet, you would hear it. It would go donk, donk, donk. He or she would not hear it, but you would hear it. And on top of that, if you were to clap in space, there would be sound, just not like we would recognize. What happens when you clap in space? The energy goes through you. Yeah. When you clap, you might notice you feel something. Same thing with space. If you clapped, there would still be sound, just not sound that you would recognize. It would be the energy of the sound going through you. So where do we find elastic collisions? There's only one place. Close. Very close, but no. I'll give you a hint. It's really, really, really small. Yeah, atoms and molecules. Molecules are pretty much the only place you're going to find that collide elastically. Okay. So here's a simple diagram. Yes?
Do the Newton's cradles ever just stop by themselves then?
Yes. Because every time they hit together and they make a clack noise, they lose a little bit of energy.
How long
And
does
then-
that take to happen though?
Depends on how big it is and how good it is. Additionally, the little twine or string or wire that holds them up, that's rubbing. So there's friction there, losing energy there too. But yes, eventually they would wipe themselves out just from loss of energy. Just like this guy. If I took the battery out of this, there's a battery that's basically, it's an electromagnet which causes it to keep moving. If I took the battery out, it would eventually peter out just from friction. Okay, here's a simple diagram. So you got M1 cruising along with a velocity v1, and M2 cruising along in the opposite direction with a velocity of v2. M1 is larger in mass than M2. The total momentum is P1 plus P2 in vector quantities. So looking at this, how does the sum of P1 and P2 relate to P1 or P2? In other words, the way we think about this is the magnitude of P1 plus the magnitude of P2 versus the sum of P1 and P2, how does the sum compare to the magnitude of the sum? It's going to be smaller, yeah, because they're in opposite direction. Sum of the P1 vector is in the opposite direction of the P1 vector. So afterwards, M1 slows down and M2 goes back in the opposite direction. And if you like formulas, here's a formula. M1 V1 plus M2 V2 equals M1 V1 after plus M2 V2 after.
You want to start that down?
That's up to you. If you like formulas, there you go. There are lots of there's lots of momentum formulas. I will warn you though, when you're at home studying for studying your momentum, refreshing yourself, if you ever find this, B prime or P prime, the prime is the same as final or after. It's just an old way of writing it. I like to use final because the College Board likes to use final. But I was taught it would be like prime, prime, meaning after the collision. So should you find that out. Okay. Any questions so far? Oh, sorry. You got it? I got to tell you, when I was your age, this is how fortunate you are to live in the 21st century with me as your teacher. I'm absolutely being serious. When I was your age, in physics, I got to use one piece of physics equipment. One, the entire year. We did one lab the whole year, and it sucked. That piece of equipment is right up there. It's called an air truck. And basically, it's a big aluminum piece of V with little holes in it. And you hook up an air supply, and air blows through, it goes the whole time. And air goes through these holes and basically acts like a hockey table, an air hockey table. You played air hockey, right? Little holes. Same kind of thing. So these things up here are gliders, and they glide almost frictionless. We didn't have these. We didn't have nifty dynamics cards. Oh yeah, inelastic collision, sorry. Inelastic collision, this guy has energy, this guy has energy, this guy has energy. What happened to the energy? it went away to the friction in here. The little pieces of Velcro got warm. Ooh, they're hot. Yes. At the molecular level, they got a little bit warmer. All that energy got arrested into heat, just like that. Oof. But anyway, yeah, we didn't have these. But these are air tracks. Now, when we're doing a momentum exercise, this is what we do. This is what you should write down. We make a little chart. We say M1, V1, P1. M2, V2, P2. And then below P1 and P2, we write P total. So what's going to happen is I'm going to press play, and the green glider is going to bounce into the blue glider. And since the green glider is more massive than the blue glider, what's the green glider going to do? It's going to follow it. It's going to chase it, right? Okay, so we got the mass, velocity, and momentum of the first object, which in this case is the green, and the mass, velocity, and momentum of the second object, the blue. So what is the mass of the green object? 1.0 kilograms. Velocity of the green object? 1.0. Momentum of the green object is normally 1 times 1 equals 1. The blue object has a mass of 0.7 kilograms, has a velocity of 0. It's at rest to begin with. So in this case, we would say the target car is at rest. So what's the momentum of the blue car? 0. So the blue car has a momentum of 0. The green car has a momentum of 1. What is the total momentum in the entire system? Yeah, 1.0 kilogram meter per second. I just added P1 plus P2 to get P total. Next, I write P1 final and P2 final, and then V1 final and V2 final. Can you see that past the balloon? Move down a little bit. Bye-bye, ammonia. Okay. Now I'm going to have them collide. There we go. So now we have the velocity of the blue car at 1.1765, and the velocity of the green car at 0.1765. What's the momentum of the blue car? Sorry, green car. What's the momentum of the green car? What's velocity times? Why did I not put a mass in here? That's the same. So what's the momentum of the green car after the collision? Yeah, it's the same. 0.1765. What is the momentum of the blue car? Maybe we should calculate. Doesn't your calculator make noise? 0.8235. Okay, close enough. Did the overall momentum change? Is 0.1765 plus 0.8235 equal to 1 plus 0? Yes, they are. Did the momentum change? No, it didn't. Okay. This is an elastic collision, even though it would clap. I'm going to rewind. Rewind. Now I'm going to make an inelastic collision. We're going to have them stick together. What mass do you want to make the blue car? Your options are 0.7, 1, and 1.4. 1.4? All right, we're going to make the 1.4. Does everybody complete this? We're going to make another one. second car is now 1.4 kilograms. It's still at rest, and it still has 0 units of momentum. So the overall momentum is still 1.0. But now we're going to have an inelastic collision where the two objects stick together. In other words, it's going to do this. Like, I'm at rest. Here I come. So here's the cool thing. Because they become one object, we don't need a P1 final and a P2 final, and a V1 final and a V2 final. All we need is a P1-2 final and a V1-2 final, because they're going to stick together. So, P1-2 final. Sorry, looks like it is V1-2 final and P1-2 final. So, if the two objects had 1 kilogram meter per second of momentum to begin with, how much momentum should they have afterwards? It's not a trick, just 1. They should have 1.0 kilogram meter per second afterwards. And using that information, now we have a mass 1, 2, that is 2.4 kilograms. We can determine how fast they should move away. So see if you can figure out how fast they should move when they collide with each other. That's 1 unit. Anybody have an answer? How fast they should be moving? They're going to go clack, stick together, and move together as 1 unit. That has a mass of 2.4 kilograms. How fast should that connection move? How much? 0.4166 meters per second. Let's see if we're right. So, here we go. Bam! Were we right? Yeah! Hooray for computer simulation. If they were the same mass, and they stuck together, if they started at 1, what should they end at? Half. Yay. Okay. Simple elastic collision.
Oh, no, why? Oh my god.
Why would you?
I've done that. Not with a guinea pig.
That's a guinea pig. That's a guinea pig.
Yeah. You're supposed to do it with like a golf ball or a tennis ball.
Does she catch it or?
No,
Does she catch it? Look how fast it launches. It's probably embedded in the ceiling.
In space.
No, guinea pigs are pretty tough. It's probably fine.
It's probably fun.
Yeah.
It's
Okay.
probably never gonna let you hold it again.
Everything always does.
With the remaining 3 minutes, consider this. A bowling ball that is 6 kilograms is rolled at 10 meters per second. How much momentum does the bowling ball have? 60. You can do this in our heads, 60, so 6 times 10. So that's 60 kilograms, meter per second. The ball strikes a 1 kilogram pin at rest, causing it to move backwards at 20 meters per second. How much momentum did the pin absorb? It started motionless and it moved back at 20. So it went from 0 to... It went from 0 to 20. So the ball is 1 kilogram, and it goes from rest to backwards at 20. So the momentum of the bowling ball was how much? 60. The momentum of the pin was 20. So my question for you is, with the remainder of a minute and a half, how fast is the bowling ball going after it hits the pin? Yeah. 60 minus the 20 transferred to the pin gave it 40 units of momentum after the collision. It came in at 60, it transferred 20, leaving only 40 for the ball. 40 divided by its mass, 6.6-ish. We'll pick this up again tomorrow.